Okay, so we're looking at bond data here. And what we're going to do is this is going to get turned in at the end for a formative grade. All right, just a small one, like 5 points, no big deal. Okay, so the table shows several different acids and bases. All dissociate, and remember, dissociate, break into ions. Dissolve, break apart, right, from each other in water. But for some, their dissociation is reversible, and this is represented by those 2 arrows going back and forth, if it's reversible, all right? And for others, it's not reversible, and that's represented by 1 arrow going straight across. There's no going back. You can't go home, all right? Use this table to answer the prompts below. So what I want to focus on before we head into the table is I want to focus right here. Strength of bonds holding the hydrogen or the hydroxide. Now, if it's a high strength of bond holding the hydrogen, then that hydrogen will not be released that easily because the bond holding it is really hard, really strong. And if that's the case, then the acid won't really be produced. Because remember, pH is the measure of the floating around hydrogens. And the higher the number of floating around hydrogens, the lower the pH. So if the other atom is holding really tightly to those hydrogens, then not very many of them will be released, and the pH will be higher because there won't be that many floating around hydrogens. Does that make sense? Yes or no? Help me out. Help me help you. Yeah? Okay, good, thanks. So let's start with the one we've been focused on, which is carbonic acid. Right here's carbonic acid. That's the one we've actually been focused on, right? And the strength of holding on to those hydrogens is high. So that carbonate is holding those hydrogens very tightly. It is not going to let go of them very easily. And so because of that, it has a reversible arrow, which means any hydrogens that it lets go, that carbonate is going to be like, no, I don't think so, and pulling them back. But like herding kittens, some of those hydrogens will get away. So there will be some hydrogens floating freely, but not very many, because carbonate will do its best to bring them back. Okay? So it will be reversible, but there will be some hydrogens floating freely. And here is the simplified equation. And here is the more complicated equation with the bad water particles, the acidic water particles. How are we doing? Okay so far? So when we look at this pH, the pH is not close to 1. It's not close to 7, but it's not close to 1. So we would call this a less acidic particle, right? Because it's not dumping those hydrogens in. And we would label this as a weak acid, because that carbonate is going to pull those hydrogens back. All right? Now, let's look at hydrogen iodide. Well, this is iodic acid, hydrogen iodide, hydrogen iodide, iodic acid. Iodide has a low grip on those hydrogens. So in other words, basically, iodine doesn't care whether those hydrogens, what they do, where they go. So there's a huge number of them that are floating freely, right? And so for that, we have a one direction arrow zipping moving over to the right, and nobody cares. None of them are going back. Here's the simple equation, and here is the actual equation with the bad water particles, the acidic water particles. Everybody all right? Hopefully some of this is being like, yeah, there it is, the acidic water particles, right? Notice the pH. Very low, yes? So that would make this more or less acidic? Yeah, more acidic. And so we would call this a strong acid. So see what we're doing here, just to be clear, we're tying the strength of the bond holding the hydrogens to the reversible or non-reversible reaction, to the more or less acidic and the pH, and then is it a strong or weak acid, yes? Do the next two by yourself, please. Okay, so in other words, if it has a high hold on the hydrogens, it is reversible. If it's reversible, it's going to be closer to 7. Closer to neutral. That makes it a weak acid. Are there any questions on these so far? Okay. See how this is all starting to come together? I hope you're all starting to see that, like, you've learned a lot and it's all starting to come together. I hope that you're starting to see that. Next. So we don't give you the equation, the actual equation, because when we add water with the hydroxides, it gets really sticky and kind of like there's a lot of questions that could go along with it, so we don't want to complicate it. We just want it to be kind of straightforward. So a low hold on the hydroxides for barium. So there's going to be a whole lot of hydroxides out there, right? Because there's a low hold, low strength. So that means we have a single direction arrow. Nobody's going back home. That means my pH is that a high pH or a low pH for a base? High pH or a low pH, Linda? Yeah, that's a high pH for a base. pH goes up to 14. So that is a high pH for a base, which means this is more basic, and this is going to be a strong base. You guys are doing great. Now we have mercury 2 hydroxide. So this is highly holding on to those hydroxides. So look, we have that reversible arrow. Now this barely even changes the pH from neutral. Is this less basic or more basic? Less basic. And that means that this is a weak base. Do the next two on your own, please. Okay, are we ready? Are there any questions? No? Everybody's good? Okay, the last thing I want you to do, and then you're going to write your name on it and you're going to turn it in. Write the pattern that you see between the pH of the acid and whether the reaction is reversible. Between the pH of the base and whether the base is a strong or weak base. All right? 2 patterns, 1 sentence each will be fine. Once you have written those 2 sentences, write your name at the top. The date is 3/26. All right? And then you can turn it in, get your phones, and we are finished. Thank you.